USIM PAC is a simulator dedicated to mineral processing, using tools and vocabulary of mineral processing engineers. It can be used for designing new plants at preliminary stage or from pilot plant operation, or to optimize and adapt an existing plant. In this demo, we will have a look at the preliminary design of a gold ore process. The first step consists in creating a project and an empty file. In this empty file, we are going to draw the flowsheet of the future plant. The flowsheet is the first of the 4 types of data we must input for running a simulation. Through the data menu, we open the flowsheet drawing window, in which we find a toolbox. We start drawing the equipment using an icon library. This step just requires the mouse. The icons are grouped by families, such as crushers, grinding mill, or solid liquid separation. Then we can draw the streams between the icons, leaving from output areas and entering the red icon zone. Colors and size of lines can be modified, and names can be easily given to streams and nodes. These names will be displayed later in other interfaces of the application. Once the flowsheet is ready, the second step consists of defining a circulating material. This material model will be used for describing all the streams. We define the different phases from predefined ones. Here, the gold ore, the leaching solution, and the activated carbon. For the ore, it is possible to define the numbers and characteristics of size classes. The gold component will be described in gram per ton for the ore and in ppm for the solution. We define then the pulp as the combination of gold ore and solution that will allow displaying pulp volume, percent solids and density in the stream description table. As a third step, all the feed streams must be then initialized. We input 100 tons per hour of humid ore. We can then input the feed size distribution and the gold content of 7 gram per ton. We then input the flow rate of carbon for stream 11 with 50 gram per ton of residual gold. The fourth step consists in defining models for each operation. At this stage, performance models, called level 0 in USIM PAC, are used. They allow the user defining the performances he wants for the future plant. These performances can derive from lab tests or, at very preliminary stage, from literature or simply user's experience. For example, the level 0B model for endocyclones describes partition curve parameters, bypass and imperfection. The DAT of the overflow is also defined. We define then the recovery we want to obtain at the leaching stage, and the performance of the adsorption in operation through the percentage of gold to be adsorbed and activated carbon. Finally, we fix in the technical model the pulp percent solids we want to obtain for the final tellings. Once we have input all the data, the direct simulation algorithm will allow the calculation of all the intermediate streams. For example, here, stream 3, the rod mill feed. We can also draw the size distribution of this stream and add other stream distributions. The calculated mass balance represents now the objective of the future plant. This is why the file is renamed target.up3. This mass balance will be used for calculating equipment sizes. We generally fix some parameters and calculate the other ones. For grinding mills, we are going to fix the load of grinding media and the length-diameter ratio. We will then calculate the diameter. For leaching, we fix the number of tanks and we will calculate the tank volumes. Some models can require some lab test results such as leaching or adsorption kinetics or settling curves. To calculate equipment sizes, we must first replace the performance models by more advanced ones, taking into account sizes and settings, called level 1 or 2 models. Then we input the fixed values for each unit operation. For leaching, we fix the number of tanks and input the kinetic parameters. For the thickener, the curve parameters are input and we fix the percent solids for area calculation. For the ball mill, we fix the length-diameter ratio and the load of balls. Using the sizing algorithm, we are now going to determine the rod mill diameter. From the rod mill menu, we run the sizing tool. We select the diameter parameter. We're going to determine this diameter with a precision of 10 cm. 51 simulation will be run with diameter values between 0.5 and 5.5. For each simulation, mill input will be compared with the target file. We do exactly the same with the ball mill and find a diameter of 3.6 meters. Using the same principle, we determine the volume of each leaching tank. And we do the same for all the other units of operation. When the main equipment sizes are calculated, we run another direct simulation to check that the project objectives are reached. Different points are controlled. We check that the hydrocyclone partition curve is similar to the one defined in the target file. We also compare the ball mill feed and discharge distributions. Here again, the simulation results are compared with the objectives. In the global result sheet, we compare the ore flow rates in target and for the calculated plant. We observed that the circulating load is in the same range that the objective one. We then observe the recovery of gold in the tailings. Around 5% in tailings mean an overall recovery of around 95%. Percent solids regulators calculate the amount of water to be added or removed to maintain a given percent solids. The sum of the three water addition streams for the rod mill, for the hydrocyclone and for the ball mill give the total water consumption for the plant. It is then possible to play with process water recycling to adjust the consumption. We finally observe the content of gold adsorbed and the activated carbon. Additional operating parameters are calculated by models such as power consumption for the mills or pressure drops for hydrocyclones. It's also possible to control the gold flow rate in each stream through bar graphs. Finally, we estimate the investment cost of the circuit. Based on mathematical models, the cost of the main equipment is calculated. Tables can be manually modified. From the main equipment cost, ratios are used for calculating the overall plant investment. Currency can easily be changed. Costs calculated by the models are updated using the Marshall and Swift Mining and Milling Index. The accuracy of such cost calculation, if not very high, however, allows the comparison of several plant configurations.